Representing motion information. This time encoding from velocity versus time to displacement versus time. We got v versus t going to d versus t. So here we are. Things are a little bit different though. In this time round, what we have is the velocity versus time graph up here, and down here is the displacement versus time graph. Also, something that's a little bit different is this equation over here. I've actually solved this for the change in displacement. If I solve the last equation, simply we get delta d equals velocity times delta t, time. All right, and that's actually going to help us immensely in encoding the velocity versus time information here to the displacement versus time information down here. All right, so let's take a look at the velocity versus time graph for just a moment. In the first interval, which is 5 seconds, we're at a constant velocity of about 5 meters per second. And that interval, is 5 seconds. So every second that goes by, the distance traveled would be 5 meters. Okay, so at the end of 5 seconds, we're going to be moving a 25 meter total distance in here. So this is actually going to be 25 meters. All right, that's pretty simple. The units work out as well. What we would have is the constant velocity of 5 meters per second times the time interval. The change in time is 0 to 5 seconds, and so what we have there is times 5 seconds. Okay, the units will cancel out, leaving our answer of 25 meters. So what happened here is that the motion moved at constant velocity, and we ended up at 25 meters. So what I'm going to do is actually try and put a little dot at 25 meters, which is about over here on the displacement versus time graph. There's an interesting way to look at this. Now, prior we've been looking at slope as a very important feature of the displacement versus time graph. Well, it so happens that another feature is also really important about graphs. Not only slope, but sometimes, and in this case, for sure, area. Area is very, very important as well. And so, really, if we look at this object over here, this whole thing that's bounded by the origin and this zero displacement line, or sorry, zero velocity line, we have this box. Now, the area is pretty simple. Area of a square is base times height. The base is 5 meters, right? That's a 3. 5 meters, like that. And over here, the height is 5 as well. So area, which is base times height, b times, oh, I know I like this one, base times height, is going to give us the displacement. And the reason is because of, again, because of the units. If we look at our axes, over here, velocity, the height is meters per second, so that's the h. So we have meters per second over here, and the base is in seconds, and that's over here. So base times height, units cancel out, gives us meters, which is the stuff that we want. Okay, so that's all good. Now we've got not only slope giving us information, the rise of the run, but sometimes area does as well, which is really pretty interesting. Now, if we look over here, what is the area of this? Well, we can see that there's no velocity, and there's nothing that this bounds relative to the zero line. In other words, this has no area. This is just a line right over here. And so we have actually not moved because there's no velocity, and therefore what happens is that we will remain in the same position. No area, no displacement. All right, so we put another dot at the same location, but I'll try to get, and we do a green one just to be consistent right there. That's not green. Oh, we should the big green. We want the green one. That's still orange. Well, we'll go back and fix it green. Oh, there's a little bit of green. It doesn't want to listen. It just likes orange. Oh, there's green. Hey, there it is. Okay. So let's do the next interval. I could go in a 5-second interval. There's nothing wrong with that from 10 to 15 seconds, but I'm also noticing that over here, the velocity is a constant -8 meters per second. And so what happens is that I can look at this whole entire interval, which is from 10 to 20 seconds. So really, what I want to analyze is the entire area of this bigger box over here. Let me clean it up so we can see it just a little bit better, like so. Okay, here we are, and what I'm going to do is color this in. That guy here, this big box, is the area that we want. What is the area? Well, area again is base times height. All right, the base is this over here, which is 10 seconds. All right, 10 seconds. And the height is going to be the velocity, meters per second. And it looks like it goes to -8. So we have -8 meters per second. Overall, we get a displacement of -80 meters per second. Like that. Okay, now that's from our prior position. We were at 25 before, so that means we're going to, at the end of this 10-second interval, we're going to be at -55, which is, oh, let's try to do another dot right about here, and I can move that guy over perhaps a little bit, help us out, and it's not wanting to move over. No problem. There, we can move it over like that. All right. Okay, so that was a negative velocity, which means that we went backwards, and so our displacement was also negative. All right, so we've got one more interval left. So let's clean up the board here, and we're looking okay. Now we move at a positive velocity from here to here, which is from 20 seconds to 30 seconds, moving at a positive 2 meters per second. Now what's the area of that rectangle? All right, again, it's base times height. It's a simple area like this. So what we're going to do is look at the base. The base again is 10 seconds. All right, so base times height, and we have 10 seconds times the height, which is 2 meters per second. What that means is we have 20 meters. All right, so during this interval here from 20 to 30 seconds, we're going 20 meters in the positive direction. All right, so where does that bring us? Well, that'll bring us 20 meters from -55. So we're going to be at this location over here about -35. And here's our point right there. And let's move that across. All right, so I've got all the dots, but I'm not quite finished yet because I would like to connect these dots. Now that they represent where we are, we got to represent how we get there. What is our motion? And it so happens to be that we have constant velocity in every case, which means our slopes will also be constant. All right, so here we go. I'm going to grab a tool that's going to allow me to do that. And a nice line tool is what I prefer when it comes up, because it's going to be really ugly if I draw it. But it's not coming up. Doesn't want to. I've got it now. All right. Sometimes the tools behave, sometimes they don't, but we're getting used to this. This is looking really good though. And okay, what I like about this is that the slopes look really, really clean. All right, and so this is it. Done. We got it. Look, we have a constant velocity over here of 5 meters per second, represented by this constant slope. A flat slope of 0 meters per second from 5 to 10. Then a slope of -8 over here, and a slope of +2, and we end up at our displacement away from the origin of -35 meters. All right, we did it. We did it. It took a little bit of finagling, but we got it. So the big concept, the big idea of this is that area is also really, really important. All right, so that area is going to help us determine from v versus t, velocity versus time, displacement versus time. Slope and area are very, very key in analyzing these graphs. And we've done it. We've gone backwards from velocity versus time to displacement versus time. All right, thanks for hanging out. And this is Morad OUT out.